Okay, so now we are starting the chapter 2 finally. Chapter 2 is our first law. Okay, first law. And first law, we are going to introduce about concept about internal energy. That's really the sort of the energy is an idea that is important. And the cousin of internal energy, what we call the enthalpy, it will come up. And how this is being measured by what is called the heat. And this is a heat. And on the constant volume, heat on the constant pressure, this is a concept that we are going to talk about. And then when you measure the heat, when you measure the temperature change, and combining this together, right? So, there's something called the heat capacity. We are using the symbol C, and this is has something to do with heat capacity on the constant volume, heat capacity on the constant pressure, and these are the concepts that we want to cover in the first section of this one. Okay. So let me start with section 2A, which is the beginning, which is we call U is an internal energy. So I like to bring this little syringes here. There's a gas molecule confined here. Do you think that this gas molecule has an energy? Yes, it does. Because of we are at room temperature that 300 Kelvin worth of an energy. The gas molecule has a random motion that bounces around like this. Okay, and then so this gas sometimes you have a higher pressure than the external. If this one is a piston, what happened? They can move, right? So if I have anything here, this compressed gas expand and they can move and do the work for this, right? So think about this is actually very. I purposely ask you a very undefined question. Okay, this you cannot. There's no answer for this, but. Think about this. This is a real case. This is a compressed gas, and then they expand. Do you know what's going to happen to the temperature of this gas? Do you think they will stay constant, or it will go down, or go up?
Cools down.
Cools down. Who said that? Yeah. Why do you think that?
Because it's under less pressure.
Under less pressure.
And it loses energy after it pushes it.
Okay, yeah, so this is a more realistic, right? This is a more realistic scenario where temperature should go down. And another way for me to think about it is, this one has an internal energy, and that internal energy has been used to do the work to the surrounding. So it's like you ate the food, and you move yourself, right? You're getting hungry again, right? So it's the same thing that the measure of internal energy is mainly governed by temperature, and temperature should go down, right? So that's a more realistic scenario. And but there is a process called the isothermal expansion, which is the first topic that I'm going to drive here. This is very, in a way, unrealistic. Okay, this one expanded, but temperature inside remained constant. That's only possible if you apply extra heat, right? That's only possible if you do the work and eating on the way, so that your energy level is the same. Otherwise, you don't feel hungry, right? So same thing. The temperature is a measure of an internal energy, but by doing so, by expanding it, you are doing the work, which is in a form of a negative in the expansion. By doing so, your internal energy is supposed to go down if you do not get what I call help from the surrounding, but to maintain the same temperature, same internal energy level, you need to have a supply heat from the surrounding. So the first law, I like to write this first thing first. Sometimes I write this way, sometimes I write this way. Okay? And this is a special case. This is a general case. This is a special case only for ideal gas. Ideal gas do not depending on a separation between molecule because there is no interaction. In the real gas, they depending on additional term. I think the choice of the temperature is obvious that we want to keep it. You remember the peak 2 idea that I need to pick 2 to describe any thermodynamic variable? As far as energy is concerned, temperature is an obvious choice. And it's you that who will decide, do I use a volume? Do I choose a pressure? And for internal energy, I want to choose a volume. That's what most of the people do. And for entropy, they use a pressure later on. Okay, so what is the first law? You remember that I just talked about a lot, internal energy, heat, and work, right? They kind of energy transaction. So we are using the heat as a symbol Q, work as symbol W, and the U as a sort of capital letter. So this is already trying to imply they are not the same kind of class of functions. This is a state function. This is not. This is a non-state function we call path functions that depending on the process itself. And the first law itself is changing in U is governed by how many heat transaction do you have and how many work do you have. This is the first law of thermodynamics. And some people write this way, du Q plus W. Some people write du is d delta Q delta W. I like those two forms. This one is, I think the Atkins book starts not to using this wiggly delta because that's a, well, sometimes actually they use it this way too. And I like this form. But this one is actually a little bit misleading. Strictly, this D is only used for the state function because Q itself is a change, whereas U itself is a state, delta U is a change, right? So change of a state function. That's what that comparing apple to apple. Sometimes actually they kind of make it redundant by putting this one. So you just have we are going back and forth, and you just have to understand we are talking about the same thing. And then okay. So let's talk about work. Okay. Work. Work is defined. And the change in the work is, and this is what we are talking about, expansion or compression. Anything about volume change, we are talking about this. And this one is, your system is pushing against the external pressure, and there is a volume change. So this is an equation that our starting point. And then we have a lot of variation for that. So think about these syringes. I think that my previous student always remember that I bring the syringes and do a lot of demos. And this is a very lame, but it works. So you think about it, this is your system, right? And then when they do the work, for example, you just look at that. When they do the work to the surrounding, this system, which is a gas, there's a lot of small molecules, the minions are doing the work, and they're pushing this wall to the surrounding. Their opposing force is your external pressure, right? So your work is being defined by what is a pressure. So this is your system, and this is your external pressure that you are pushing against. So this is a lot of systems that they're trying to do the work, right? Everyone is trying to do the work. So you are going against that pressure to expand the volume from here to there. Small change in the volume. Okay. So somebody will say, I mean, another complicated version that probably you would not want to know is P external times A times dL. That's a force, right? And that's a distance, so therefore that's an energy, right? But I mean, even this kind of equation is hardly in any of the textbook. or anywhere. So it's not even necessary. You just take it. This one should make sense to you, and that's a starting point. And then we start to go and have a scenario here. And so that's the first equation, and I'm saying something that is pretty obvious, which is when you say expansion, we are talking about V final. Volume change is from V initial to V final, and the V final is bigger than V initial, right? In other words, the ratio between this is bigger than 1. Okay? So that's another obvious statement that we have. So let's do the two cases. So I'm going to do this. This is, I guess, a definition of this. And then I'm going to do something called irreversible. And then I have an extra one. Irreversible is not so clearly defined, so against constant external pressure. So this one is essentially constant. When your external pressure is constant, this is a sort of the same idea. Okay, the external pressure this system sees. Yeah, you're talking about 1 atmosphere pressure at the outside, right? So this one is a compressed gas in the beginning. They let it go. They start to do the work, and the opposing force is always has been the 1 atmosphere pressure. So we can see that this equation work was defined by d external dV. So now what I'm going to do is the change over the work. Or this one itself is actually just the work for that process should be initial volume to the final volume, right? So far, nothing really changed. So if I write this equation down, I can say work is minus initial volume, final volume, external dV. The question is, how are we going to figure out the external volume? I'm saying that external volume here is a constant. And this is constant. This one just come out like this. And you got this equation called very simple equation, delta V. So let me rewrite it in a simple way. Work irreversible minus external times delta V. That's probably the most simple work equation, which is more realistic than in this case here. So moving against the constant external pressure, as long as I know my volume change, I know how much of this system that we have is 4 guys who's doing the work to the surrounding. We know we can calculate the work. Okay? So first 2 question is expansion. Work is a negative. Does it make sense to you now? When you say the expansion means delta V is a positive, multiplied by minus P external, and you should have a negative work, which is a work irreversible. So that's the one. Once again, this sign comes in a little bit complicated later on. So don't assume that this work is always positive. It can have a positive or negative. When P external is 0, we call this called a free expansion. Work is 0. Oh, work is 0. So you have no work when you are moving against, and the other side is essentially the vacuum. They can just go, and actually opposing force is nothing. So that's the. So this is an irreversible. Okay, and then that's the. And then I'll go to the reversible. Have you heard about reversible work? Or this is, I mean, my job is to introduce the concept of reversible work. Is reversible work real? Do you think that can happen really? Think about it. So irreversible means this going this way, right? Irreversible means they can go any way, right? So it's kind of hypothetical state. What that means is, think about it, if I have a high pressure, my external pressure is controlled by additional force down pushing this piston, and in the beginning, this is a expansion. That's an expansion. What I did here is I'm kind of adjusting my external pressure extra so that the internal pressure is same as your external pressure. If your internal pressure and external pressure is the same, they cannot expand, right? They cannot expand. But it is a hypothetical reference state where we can calculate what is called the maximum expansion work. And I will explain you to do that. So just simply speaking, this is a quite popular topic, reversible expansion. Okay, so this is a reversible expansion, and then I'm going to say particularly I want the isothermal expansion. I told you about isothermal expansion is actually when the expansion happens, temperature is supposed to go down if you do not supply extra heat. But somehow I made it happen so the temperature remains constant. So let's talk about it. So the most important concept of reversible is external pressure, which defines your work, is same as your internal pressure of your system. And we are not using this symbol, we just say P. Okay? So all of a sudden that the equation, the work, or the, let's say, I don't like this expression, so just say work is a minus external pressure, and when you change the volume, so the pressure times volume